So good afternoon, everyone. And I'm glad to see many of you have managed to make it this afternoon. So it's my pleasure to introduce my close colleague, Mark Nicholson. So Mark is a dedicated educator with 30 years of experience of safety critical systems engineering. He has provided consultancy to a number of organizations in many different domains, and he has been heavily involved in standardization activities, particularly focusing on safety in a number of domains. He is currently the education lead in the Assuring Autonomy International Program, the AIP. He is also a director of the UK's Safety Critical Systems Club. At the moment, his research interests focus on the concept of data safety and how to embed this concept within current safety processes and future robotics and autonomous systems. He is also investigating the skills barrier to safe adoption of robotics and autonomous systems, particularly within the Assuring Autonomy International Program. And this afternoon, he's going to tell us more about the assuring the safety of resilient robotics and autonomous systems with a focus on the current capability and evidence requirements. So Mark, we're all yours.
Thank you very much for that. Just let me do the share thing. And just because it worked 20 seconds ago doesn't mean it's working now. So hopefully you can see my slides. So thank you very much, Ibrahim. As Ibrahim said there, just trying to think about the current capability and the evidence requirements relating to the assurance of safety. I've got a quick agenda here. If at any point you want to ask a question or throw bricks at me or whatever, please feel free to do so. Since it's virtual, they won't hurt too much. So first of all, I'm just going to very quickly run through what I believe is a common understanding. So I'll just talk about the definitions and assumptions we're currently making about robotics and autonomous systems. I'll talk a little bit about the current state of the art for the assurance of safety critical systems that incorporate a significant software component to them. And within that, we have something called the 4+1 principles. I'll then talk somewhat about how those principles, how those approaches are challenged by robotics and autonomous system safety assurance, so the disruption. And then I'll talk a little bit about how the AIP and other people have started to try and address those issues and the sorts of pieces of evidence that we're going to have to produce in order to make sure that we can provide an appropriate safety case for those. So that's the elements that we're going to have a look at today. As I say, if you've got any questions, please shout them out or put your hand up, and I'm sure Ibrahim or Radu will spot them and do the appropriate asking. So just to be on the same page, robotic systems, the physical manifestation of autonomy, we're trying to get these systems to provide some tasks. Those are cost-effective tasks, hopefully, that will have some benefits to society, as you can see across many, many domains there. From a safety perspective, there's actually two characteristics, two aspects we've got to think about. The first is that those robotics autonomous systems are being provided explicitly to improve safety. So that's the job of them. What we're actually wanting them to do is to work in environments that human beings were in previously, or some other reason why we think employing them will actually overall improve safety. And a lot more systems will be interested in providing the service we want to provide, so the social care or the factory capability or whatever it happens to be, but safety comes as a side effect. So we'll have to persuade ourselves that we've done a good enough activity to cope with those side effects, that reduce the risk to an acceptable level of those. So we need to think about both of those, and we're going to have to work out what we want the safety to do, what we want the system to do with respect to safety, and how we're actually going to show that we've got appropriate levels of safety embedded in there, and can persuade ourselves and other people of that. So robots, the physical element of that, we could have a number of models, ways of actually representing that. I'm just going to assume that we're using something like SUDA, so the sense, understand, decide, act framework. We all know there's many more of them that we could use, but essentially they've got pretty well the same sort of characteristics to them. And more importantly even than that is these things are not just a one-off activity, they're an ongoing interaction with their environments that they're embedded within, and they've got to be able to cope with that through a period of time, even if that environment changes, warps, adapts, or whatever within that. So just going to use SUDA as our baseline model. We're going to assume that they're autonomous, so they have some capability to make decisions, and that's different to current systems, of course, and that have very limited coded ability to make those decisions. I'm going to assume that we're going to use machine learning for elements of that, in particular supervised machine learning, and essentially that we're going to turn whatever model we produce from the data into some sort of software and try and embed it in our system. The machine learning, the two elements that we're particularly going to have to assure ourselves that we've dealt with well is that the machine learning component is able to help us develop models of the real world, of the world, from the sensor data that are an appropriate level and say the right things to us, and that we're going to be able to choose between those alternatives to optimize or produce at least a safe action that we're going to need. So that's the understanding and decision-making element of machine learning. So presumably so far, there's nothing surprising there. Has anybody got any surprises about what I've put together so far, or does that all make perfect background sense?
Yeah, all is fine, Mark. Yes.
Good, that's what I thought. So moving on to the next bit. How do we currently assure software-intensive safety-critical systems? Well, essentially what we do is we start developing a system and we try and embed good safety within it. We've got stakeholders involved while we're doing that, the suppliers, the manufacturers. We've got some sort of safety assurance process that's running throughout that development activity, and that's building as evidence as we go, but also building in an appropriate level of safety. And of course, historically, we've used models like the bow tie model to try and get our heads around that. So we've identified a set of hazards. We then put barriers into place to try and stop failures within inside our system, leading to those hazards and eventually into accidents. Eventually, we'll get to an endpoint where we decide that we've done enough against that, the level of risk is an acceptable level of risk, and we'll produce a safety case, a set of argument and evidence that persuades ourselves, but also other people, that we've got an appropriate level of safety built in. So we'll have to persuade the standards bodies, the regulators, etc., that we've done a good job against that. And assuming we can, we'll put it out into operation. The only time we'll challenge that is if we decide to do a new model of our car, or we actually have an accident or an incident which will challenge our safety case. We'll go look at what went wrong, go back to our design process, reapply our safety assurance process, and that will then allow us to put a new variant on a theme out there. So we're very reliant on these safety assurance processes to persuade us that we've done a good job against safety and got an acceptable level of safety. And those are actually pretty mature at the moment. We spent 30 years on them for software intensive systems. And what I wanted to do really was to start thinking about those and try and look at the characteristics that we're assuming within those, and the sort of evidence that we'll need to produce about how we've challenged them, and then of course how we're going to deal with those. So here I've just introduced a standard, which on the right hand side is a diagram of the flow chart for what you need to do as part of this aerospace recommended practice for current large aircraft systems, particularly safety critical control systems like avionics. And I've broken that into 4 bits. And I think the 4 bits, as we'll see in a minute, are all challenged by what we're trying to do here. So the first of the bits is currently, if we're going to produce an aircraft, we know what we want from that aircraft. We know what the needs are. We know what the capabilities we want from that are, particularly the capabilities for good safety. We know the operational environment that it's going to work in. We've got a good profile for that operational environment. We even know what good looks like with respect to safety. So we have acceptable levels of safety risk. We know how to interpret what we've actually got against those levels of safety risk. So right up at the top, we've got some good work around what good looks like, and I've sort of coded that with a red blob, and we'll come back to that later. We then start working through the development process, building of architectures. So to do that, we undertake typically a top-level aircraft architecture, which involves the functions, the services we want to provide. We decompose those down through system subsystems, and eventually we allocate them to individual bits of software and hardware through the process. And of course, for us, the important element there will be relating to the software, but also because the decomposition itself is important, and how we do that and how we persuade ourselves that's providing us with good, we can get good evidence that we've done that well, and it has the right characteristics associated with it. There we go. So that's the blue bit. We've then, because this is all about safety, we've then got a set of safety processes that we put into place to, at various points, check that we've done a good job, that we're heading in the right direction, that the final outcome will be acceptably safe. And as you can see here, there's a number of different techniques and approaches, and they're all producing evidence for us that we're going to reuse at the end of the process to persuade ourselves and other people that the process found errors, took them out, and therefore the safety characteristics are going to be as we expect them to be. And finally, this particular standard calls what they call an aircraft safety assessment. In other places, it's called a safety case. And there essentially what we're doing is saying, what persuade us? What's the arguments? What's the evidence associated with the final implementation of this system in its against its assumed capability, its operational profile, what good for safety looks like? Persuade us that you've done all that the process hasn't left anything in there that's inappropriate, and you've got the right evidence over the final product. So those are the 4 basic elements. And if you look at all the different standards, although they'll tell you to do it in different ways, they all end up having the same sort of elements to them. So far, so good. One of those key elements, of course, is the software element. And over the last 30 years, we spent a lot of time and effort trying to assure the contribution of the software component to the overall safety characteristics of the system that we have. And eventually we've managed to hone those down into just 4 principles. And then we've got a sort of rigor one, a proportionality one over the top of those. So we alter the amount of process effort we put in and the evidence against that process that we can generate, dependent on the level of risk that we've had. So as you can see here, we start off with a set of safety requirements, which we decompose down onto the software components. And if those software components have the right characteristics, they will contribute appropriately well to safety. We then develop the software architecture, making sure that the decomposition of the requirements doesn't actually break that original software requirements element. And so we'll break that down, trying to make sure that as we do so, we can work out how to bring them back up. We'll then show, of course, when we've finished, that the software safety requirements have actually been met. But we may have introduced some extra safety effects as we went along. So we look for any side effects, any hazardous behaviors that aren't relating to those original requirements, but just by the way we've done things, just by the implementation, we've introduced some new safety problem, and we want to look to see if we've mitigated those. And we do all that work proportionally, produce all the appropriate evidence proportionately against that. And down the right-hand side here, I've just given a few pictures of accidents and incidents that have been traced back to these different requirements. We've had accidents resulting from poor decomposition from higher level system requirements to lower level requirements. We've had accidents relating to an inability to actually meet the requirements that we set from ourselves. We've had side effects that are going on from that, and so on. So all of these are now, how should I put it, grounded in actual reality on the ground in different systems where the software has contributed to those. And so we've got a mature level of capability against that. So that's where we are currently. It's all about identifying the safety requirements and then decomposing those safety requirements, producing evidence over the process and the final product of that against a set of principles using fairly mature guidance and standards. So I guess this is my next question. Has anybody got any questions at the moment about those existing circumstances?
Can I just ask a quick question, Mark?
Yeah, go on.
Do you have any comments on the problem of combinatorial issues? So having done the decomposition down to software, how we then consider the fact that they all interact? Where's that picked up in that flow?
Right. Okay. So that's an interaction. So you're right. The standards tend to assume that there's some atomic elements that you can do. So you can actually propagate these down to independent components. That, of course, in complex modern systems is just not true. We try very hard to keep it as true as we can do, and then to produce models over the interactions that we're expecting to happen as a result of those. You're right, then of course we say, well, we've got these individual elements, these individual components, and as long as their environment is as we expected, as long as they interact with the other elements in the system as we expected, then those safety properties that we put forward will hold. But that means, of course, we've then got to check that when we put it back into the development of the overall system. So it's not just a matter of the individual parts, it's the complex parts. And that's one of the major challenges at the moment for complex safety critical software-based systems. I absolutely agree to you, if this is the underlying question, that this is going to be even more difficult to show that we've managed to keep these separated for the next generation of systems using ML and things like that. And one of the areas that's particularly true at the moment, I think, is that integration, how to do these by contracts and all that sort of good stuff, but also the operational phase. I think it's going to be really challenging because we know that we can't get to a good level of understanding for modern, very complex systems, and we're taking those interactions further. One of the areas I've got is we've got all this data. If we reuse the same pieces of data in multiple ML components, because that seems to be appropriate for this single unit, what does that mean overall, for instance? So our common cause issues and things. Was that the underlying question?
Yeah. Thanks, Mark.
Yeah. So all the work that the safe complex engineering people have been trying to do on characterization of complexity all hold here, I think. Any other questions? Right, okay. So my view is that robotics and autonomous systems, as we started to talk about there, actually disrupt all the four major bits of systems engineering and system safety I've been talking about. This would do if you will allow you to actually, there you go. So I said we knew what the operating environment was like and that we could characterize it well. I don't think we can. As we move from these bounded closed world systems like the wonderful nuclear power plant system I've got up on the top right, towards the very open world, our street in Vietnam, characterizing what the operating environment looks like is going to be a really challenging, and producing evidence of coverage across that, of course, will be a really challenging part. How are we going to do that in the short term? Well, we're going to go through a set of restricted defined worlds. And that's, we're going to have to produce evidence of that is a reasonable defined world, that the A, that we've done well against that defined world, but B, that the defined world itself is acceptable, and that we know what to do when we get outside of that defined world if we actually reach it. And that'll be part of the operational monitoring. I also said we knew what good looks like. We knew pretty well what we were trying to achieve before we started. That comes back quite a lot to the definitions of safety. Safety historically has been very much about physical harm. It is not clear that that will be sufficient in the future. We're getting into other types of harm that may have to be incorporated in our safety definition, have evidence produced against them. And of course, that means we've got to look at the ethics and what counts as an ethical capability here. And more technically, we're going to have to start looking at how we're going to allocate what is an acceptable level of safety risk to different activities and tasks and different robots. We're going to have to look at this responsibility, authority, control, and accountability, and which organization, which stakeholder is going to get which of those and to what level. And I'll come a little bit back to that with the ML in a little while, but I think it's also a much larger problem that we don't actually know what good looks like. And so, we may have changing requirements over the next few years about the sorts of evidence we're expecting people to produce. So that's right up the top. We used to know what good looks like. We don't anymore. We used to know what the operating environment looked like. That's changing. Of course, that blue area where we then defined our system, the capabilities that we're going to have to support are changing. So we've got to have evidence still around human interaction with these systems. I think that's true and appropriate. The nature of that human interaction, of course, is changing. And so we've got to think about how that changes the evidence we've got to provide and the argument that evidence shows us that we've done well in coping with that interaction. We're much more into the world of Internet of Things, integrated multiple system services. So communications are going to be much more important to us in assuring those. For instance, I'm involved in a program that's looking at the contribution of electromagnetic interference into how these systems work, and therefore potentially the safety characteristics of those. Why? Because of the amount of communication and the dependency on them in order to get good functional but also safety output. And of course, somehow we're going to have to show that we can adapt these systems appropriately when we have environmental change and internal state change, because internal states of the system could lead to hazards, but also changes in the environment can. And if you notice here, this little trio walking along here, one of them's foot has fallen off. So that system has to be able to adapt to that. How are we going to provide that capability, but then assure it? So there's multiple elements there that we're going to have to provide some work against. And we're going to have to show the system remains safe and assured throughout those processes. And then the final, probably most important one for us here, is that we're going to use a different type of component. Now, the component, of course, that we're particularly interested here is machine learning. So instead of decomposition requirements down into a software component, a hardware component, we're potentially decomposing it into a machine learning component. And that is where we get into the way that we develop machine learning. And here it's a very simple model with the 4 elements: data management, model learning, model verification, model deployment, put it out in the real world, understand how it acts, update your data, and repeat as required. Of course, we're going to have to provide assurance across the process of that, but also the final result of that. And that, building it up from data, is a very different process to all the assumptions that we're making in our assurance frameworks at the moment. But we've got to make sure that those fit into those existing frameworks. They shouldn't be completely new and different, because designers will meant to make decisions between them. They'll want to make decisions as to whether you use classical software or machine learning, rule-based, adaptive, etc. And they'll want to mix and match as appropriate within their architectures. So we've got to facilitate that somehow. What's the first step? Well, the first step is we'll need to augment our development processes and our safety processes. We'll have to start looking more explicitly at the extra capability that we're going to require of our robotics and autonomous systems. So we're going to have to start developing safe operating concepts. To do that, from that, we're going to have to identify these operational domain models to address that much more open environment. We're going to have to identify the autonomous capability that we require from that system. Somehow we're going to have to put those into appropriate requirements and build in appropriate safety. And doing that will mean requirements decompositions through our systems with that in mind. And eventually, some of those requirements, some of which will be safety requirements, will flow down onto the machine learning component. So we've got new elements to persuade ourselves that we've dealt with well within our existing framework. We're going to have to take some idea of what good looks like from that and produce an appropriate safety case associated with that. That's the right-hand side, including the contribution of machine learning. And then we're going to have to translate that into what we're going to do at operational time. So that's our, we're going to have to extend that overall system process of which, for the robotics and autonomous systems, for assurance, for which ML is going to be a part of that. Up that top left-hand corner, we will be altering what a good contribution means from that component, and what the safety contribution means. We're currently trying to work on what's socially acceptable here. That's going to change. Even the nature of what we count as safety is going to change, from just physical harm into mental well-being, harm due to social biases, and all those sorts of good things to consider. So I just wanted to think here about if you're developing a robotics and autonomous system that has potential safety issues, that's going to use machine learning in it, using our sort of model process here. What are the sorts of questions that you're going to have to ask yourselves to address those? So, you know, we're going to ask ourselves, is the data biased in some way? Because we can cause harm as a result of that bias. Is it representative of the operations? Can it be updated when we get the real world ground truth back from that? Is that process going to be appropriate to us? What about the model learning? Is the model appropriate for the problem? Does it represent the ethical behaviors, the safety behaviors that we want from it? Can the learnt behaviors be understood? And that's where all our explainability evidence starts coming from. So you're persuading people that the model that you've come up with has these appropriate properties, and that you've thought about those in development. And then, of course, we've got the classic model verification problem. You know, is the system incorporating this model mature enough to deploy? Is the real underlying question we're asking ourselves. And even if we think it is, we're probably wrong to some respect. How can we make sure that we can adequately monitor that in the real world as part of our ongoing continuing safety processes? And you know, do we have any capability of anybody to mediate those outputs, or is it completely on to the onto the modeling, onto the RAS itself? What does that mean for the level of assurance we need at the point of putting it out into service? So all of those questions need to have evidence related to them. And so we've got this safety process. We've attempted to understand the context. We're trying to build in safety and propagate it down. We're trying to build appropriate understanding of the requirements as they flow down into the machine learning component. And then we want to look at the contribution of that machine learning component into the overall system capability and the safety. And that's where one of the first pieces of work that Ibrahim and Colin and people here, Radu, were involved in, where AMLAS comes in. And AMLAS was really trying to look at the assurance of this machine learning and how making an assumption that we knew what the system safety requirements were flowing down into it. So what we've been talking about up to now up here with the identification and decomposition of the safety requirements against what good looks like, we can assume at that point that's happened. And then we've got, during development, we've got a number of workflow items to apply to that. Here's the 6 of those. From that, we will get a safety case for the ML component. Those will have to be visited a number of times during the development process. As we do, we'll get evidence out of those processes, and of course, we'll get evidence out of one final run through of that process. And as you can see, this is very much predicated on our life cycle model, where safety requirements are flowing in. The model is being developed, and then implemented back into the system context. And we've got those 6 elements for you there to have a think about. So what do you get out of the MLAS process here? Well, the MLAS process says, as you're developing your system, as you're developing your machine learning component into that process, what are the set of work activities that you need to undertake? And here you've got the color-coded set of work activities to be produced, to be undertaken. From those, you will actually produce evidence. You'll produce some documentation that we're going to use as part of an understanding of the contribution of that into the overall safety case for the system. And I just wanted to highlight a couple of things here relating to this process. I want to talk a little bit about the logs through development. And I also just want to bring us back to an example of one of the elements, which is this data management. Since after all, the ML is working over the data to produce the model that we're going to embed in our overall system. So if you look at the MLAS guidance, at multiple points, multiple steps, it has a documentation that has phrases like model development log, or verification log, or what's that one? The erroneous behavior log, the data generation log. Yeah, what is that trying to do? Well, what it's trying to do is to say you can't do this assurance of a machine learning component within a system for its safety properties by developing the machine learning and then trying to produce the evidence that you're going to use as part of the safety case. You have to build evidence as you go along. You have to be able to know what decisions you made and why you made those and why you believe the implications of those are set at an appropriate level as you go through that process. So, like in current software intensive safety critical systems, you're going to have to produce evidence that's both relating to the final product, so your verification, but also the decisions and choices and things you did during the development process. So here I've just pulled out from the guidance some statements about the generation of assurance evidence throughout the development of the system, particularly the ML component into the system, relating to the development of that ML. So it states that you should produce an ML development log, and that log says you shall document and justify all key decisions made during the learning process and how those choices impact performance or robustness, and therefore potentially resilience of the final model and the system within which it's embedded. So what tool chain did you use? Why is that a good tool chain? Why should I be using TensorFlow 3 in this particular case? What are the details of the model selection? How did I change get the hyperparameter changes to work? How did the thresholds for the trade-offs, how did I define those? How did the classification approach work? For instance, I might be interested in the proportion of false positives because that's got a potential safety impact. How did I decide how to minimize the number of false positives, etc. in that case? How did you decide when to stop doing more learning, etc.? So we're building up here an understanding of the choices and decisions were made, which had an influence on that final model, which we're then going to instantiate as a piece of software into our system. So the MLAS is actually talking at multiple places about this assurance evidence And the important take-home message in there is that that's not a one-off activity. It's an ongoing activity throughout the development process. And then we're going to take that and use it in the safety case about the contribution. So just to go down a little bit deeper, one level down in the AMLAS actually talks about the data management assurance. So it gives you a workflow there, define the data, generate the ML data, validate it, and then instantiate the data argument pattern. Ooh, we've got one of those. So you look over to the right-hand side here, and it says, here's one possible argument you could use to persuade ourselves that you've done good data management, and that therefore that has contributed appropriately to the assurance of the output of that ML process, the model that you're using, and therefore the contribution towards overall safety of the system. And you'll notice here a bunch of circles, and those circles relate to the evidence that we're expecting a developer to produce. So here we've got evidence, and validation evidence in this case, against the relevance, the completeness, the accuracy, and the balance of the data that we're using in the context of the particular system, its operating environment, what good looks like for that particular system in that domain, in its environment. So although we can give you the elements that we want you to produce, what counts as good data to back that up, there you've got to think about what that actually means in context, which is why AMLAS guidance is good guidance, but it can't be thought of on its own. You're going to have some inputs relating from that higher system level. So producing evidence in there of an appropriate quality that will allow you to show that you've validated those characteristics against the system that you're embedding it in. What you get at the end, of course, is a piece of safety case and piece of argument and evidence for the contribution of that ML component into the overall safety case. And here, as you can see, there are these evidence pieces dotted all over the overall component case. Many of those are over the final version on a theme of the model, but many of them are being produced as we go through the development process. The final model, of course, you've then got to integrate and embed into your overall system, and you've got to show that integration works well. So here we've just got an integration into an object recognition for a vehicle, object detection, object tracking, object prediction. How are you going to take the results from that, embed it in, show that that ML is contributing well within that system? And of course, there you'll have more than one ML component potentially. You may have a large number, and back to Colin's comment earlier, there's a big integration issue here, and common cause issues and all sorts of safety issues we need to consider. So finally, you'll decide to deploy the system. You've got a case for why that ML contributes appropriately to the safety characteristics, all the sets of MLs. Through the AMLAS process, you'll produce an overall safety case for the putting that RAS into operation. I think we have to accept that for the time being going forward, because of the novelty, complexity, because of the operating environment that it's working in, the baseline system that we want to put into operation won't necessarily have the same level of safety that we would expect from current systems. And even if it does, we certainly won't have the same level of confidence that that really is the safety characteristics we will have, for all the reasons that I've talked about so far. So to me, the operational part becomes vital. The monitoring and evaluation and the attempt to go round this model really quickly, should we find something, in order to make sure that we don't have accidents and the overall risk remains at a level that's acceptable to us. So from the operational side, one of the sets of things that we ought to accumulate at development is the assumptions that we've made during that development, both at the system level, the environmental level, but also, of course, at the machine learning development level. And then we're going to have to figure out how to put in appropriate monitoring against those and triggering of that to make us go back and reassess our safety or confidence in that, and then update our system as required. We will, of course, have to think about the inputs that we're getting, the data inputs. We said that the data had various characteristics to it. We based our safety on those characteristics. One of those will be the nature of the inputs that we're going to see. And of course, if we don't see that happening in reality, that will challenge our safety case. We're going to have to look at the outputs and see if we've missed things in our assurance case, in our safety case, you know, that this thing doesn't deal as well with occluded objects as we said it would be. And we're going to have to somehow trigger the circumstances under which this is different enough for us to have to look at that. And of course, that's where some of the resilience characteristics come in operational time. And so finally, what I wanted to just say here is we've been producing highly complex software-based safety critical systems in a number of domains for quite a few years now. We've got mature systems engineering and system safety processes. We don't always do them very well, but we know what we should be doing. We try to develop such we build in safety. We need to assure as we go through. As you can see here, we're starting to understand how to tweak those to be appropriate for the RAS world. And that will still require us to provide evidence as we go through the process, to provide evidence before we deploy, to keep looking at things in operation. But there are some specific elements that are going to challenge us, and we're still having to think of these not by going back to standards, by going back to specific guidance. We're going to have to think of them on a case-by-case basis at the moment. Even what's an acceptable level of safety. What the implications of how open the environment we're going to operate this system in is. What evidence we're going to need about the decision-making that those systems are going to make, what evidence are relating to the machine learning. We've got the frameworks for that, but the specifics are still going to be very case by case at the moment. And you know, we're going to have to build up how we make assurance process related evidence more dynamic for that operational safety. But I think that one's because it's pushing into the future a bit at the moment. So really, I just wanted to give a background of where we are with assurance of systems and system safety at the moment, and show you how we're starting to upgrade those and the remaining challenges that are kept through that. So at that point, I will stop my sharing and I will hand back to Idley.
Thank you very much, Mark. This was a very interesting talk. Well, we have approximately 10 minutes for questions, if people have any questions. Grisel, is there a current application that uses machine learning in critical systems, presumably successfully?
You mean as in certificated in operational time?
Yes, I was wondering if there is already an application that uses ML in critical situations.
There are some, not directly inside the system that I'm aware of for the most safety critical for inside control systems. People have used machine learning in a support role for decisions human beings are making inside those most safety critical systems. But we're very conservative at the moment about using them in direct operational control. And the first generation of them will be we will figure out, we will turn them into the machine learning final model into software, and we'll assure that final software model pretty well as we do at the moment. And the problem with that is, at the moment they'll probably fail, because we know, that the coding that we know how to do by traditional methods has got a higher level of we can validate and verify it to a higher level. It doesn't have the capability though when it's working well, and that's the balancing act that isn't very far away.
Thank you.
Right, I might squeeze in a question as well. So I wanted to ask Mark, you outlined so many grand challenges to the use of autonomous systems in safety critical applications. Do you think we are likely to see an autonomous systems winter like we did for AI? Or are we going, do you foresee we would be wise enough to deliver systems in a stepwise manner to avoid that?
If you'd asked me this 3 or 4 years ago, I said we probably are going to get a winter, because the capability imperative and the amount of money that was being pumped into these systems by people who were there to get a rate of return was very high. I think we've managed to persuade ourselves to back off from that hype somewhat. If we manage to keep ourselves to that incremental process and we don't have a couple of nasties, I think we probably will be able to do that. The problem is we're going to undermine trust pretty fast if we try to put something in too much, too quickly, and too far ahead, with too many grand challenges addressed at one point. So that's a real challenge. And the other thing is that because we're having to think our way through this on a case-by-case basis to build up our understanding of what good looks like, we will inevitably make mistakes on that. And that's part of the how fast you can identify those. That's not what we currently do because of the maturity of what we have. And that's probably the biggest challenge to fix straight away for me in terms of safety insurance.
Mm-hmm. Thank you, Mark. So Elias and then Emilia. Elias?
Yes, hi Mark, can you hear me?
Yep, certainly can.
Hi, thank you for the talk, very interesting overview. At some point, you equated, I think, the autonomy, right, with the machine learning capability, supervised learning in particular. Did I understand it correctly? And then from that point on, I'm thinking the question, are you really talking about machine learning systems, autonomous systems that employ machine learning? Are only autonomous systems employing machine learning, or can we have autonomous systems without machine learning?
The important, you're right, there's two important bits here.
Okay.
The first one is we're going to change where decisions are being made by in a system context. We're going to move them from the human to the machine.
Right.
Some of those we'll be able to do by rule-based, but that still is a significant assurance problem because we haven't given them that level of authority before, and we haven't got the checks and balances. One of the ways we will identify that actually we can address that issue is not to try to do it in rule-based, but to move it to machine learning instead. So there will be a design choice by the developer when to use classical versions on a theme and keep the capability that a classical software system can give you, where to move the decision-making into the system level via a sort of pseudo-like approach, but to base it on rule-based, and where to move it into machine learning. And part of that will be, if I understand what I've got to show within that system context, I can start looking at, well, if I put it in ML, what does that mean evidence-wise I've got to provide? Do I think I'm going to get there? Am I confident I'm getting in there? Or do I want to back off a little bit in capability because I know that I'll be able to do it by a rule-based approach? And I think, you know, that's the important thing. The reason we've always done safety over systems engineering is that safety is only one characteristic to trade off in the design space. It is not anybody who tells you that the primary thing they're interested in safety is either lying to you or themselves. What they really want is it to provide a service, a capability, and for it to be safe enough.
Right, so that it can be used, right? I was thinking in these lines also, what is the connection between and trust? The previous work I think that I've read from Radu and his team, and the new AMLAS, I think.
Well, I think the entrust one was to me was starting to try and look at that dynamic area when you're moving out. I mean, it's not the only, but it's starting to say, well, okay, if we are going to do, I mean, that radio answer, but if we are going to do go down this line, as I was saying, we're going to have a very robust operational phase that's going to have to very quickly identify issues and address those issues, because we can't rely on the baseline. We can't rely on that very high degree of confidence that we have in a current, you know, one of those new Rolls-Royce only £2 billion nuclear power plants that they're going to produce from today. You know, the software in that, we've got a very high confidence on how it will act in operation before we use it ever once in anger. Yeah? If you turn that into a fully robotic autonomous system, set it up, press go left, with lots of machine learning and all that in there, really, how robust would you think it is at the box? That's where the differences start coming in, to my view, and we're going to have to rebalance that characteristic.
Right, and it can be combined, from what I understand, from today, right? So, yeah, okay. Yeah. Okay, great. Thanks a lot. Yeah.
Right, so I think we have time for the final question from Emilia, if you want to tell us, Emilia.
Yes, thank you very much for the presentation and for the safety-related aspects. My question this time comes a bit more towards extending the safety envelope to consider ethical aspects. And even if we would have an evidence-based approach that will go along the development process, when we try to consider ethics, we have the human nature in place, which is quite contradicting of what we define as good. So we can have some type of consequentialist point of view or the ontologic point of view.
Yeah.
And how can we integrate a moral, and how can we assure a moral development of an intelligent function by looking at this divergent way of thinking on what is good and what is right? Should we define some type of ethical design domains? Or what would be your thoughts on it?
Yeah, absolutely. I think you're right. You know, the people like Zoe inside the AIP who have been looking at these things, she's saying, well, you know, which set of principles do you want? I've got 70 of them that I've seen defined so far. Pick the one you want. To an extent, that is true. What we'll do is we'll put forward we think is an appropriate ethical set to work to for that particular design under responsible innovation. We'll get agreement from the stakeholders, and that's why we need people like the regulators to be understanding of these things. And then we'll build to that and see what happens in the real world. I mean, in practice, that's what will happen, and we'll have to go around that loop. From a safety perspective, the core thing is we understood what we meant by safety. It was all about physical harm. If we're going to move away from that, we need to get an agreed definition for that for each project. Now, hopefully, we'll be able to get frameworks together that allow a project to identify what it's going to do against that, with agreement by their regulator for the safety critical domain. But you're right, there is no easy answer to that one. And one of the problems is going to be that I don't think it's going to be world universal for a while. You know, what's acceptable in America will not be acceptable in the UK, etc., etc. And so somehow we may have to tweak these systems to act differently in different places because they're going to act for different models. So yeah, absolutely, that's another emergent area.
Thank you very much. Mark, do you have another minute to answer Tim's question about the challenge with finding a ground truth to compare against?
Oh, the ground, yes, absolutely. So yeah, we always know that, you know, models are models. they're by definition simplifications. What we're doing, of course, is we're setting out in the safety case, as part of the safety case, what the model that we're building to is, and our current understanding of that. We will then, that's part of the assumption set, we will then challenge that by the real world, as long as we can put things into place to identify when that is happening and have it tagged for a trigger back into the operational domain. And one of the areas I think is most interesting to look at, and I've currently got a proposal for a European networking, is looking at operational services and how they will embed these systems in such a way that they can do continuous ongoing safety management of them. What do we need extra in order to be able to do that so that we can look at the ground truth? Because, you know, with the best will in the world, I don't think we'll be making a judgment that we've done as best we can to some degree of rigor against that at design time, but we won't have got that right. And we'll have to adjust that via monitoring and management over it.
So Colin, did you want to very, very briefly?
Yes, it is very briefly. Amelia, your question I thought was a fantastic one. I just wanted to say, I read it as two bits. I don't disagree with anything Mark said. The first was really exactly as Mark said about getting the specification right. Incredibly hard to say what it is we want to achieve. But there is a question in there, shall it be evidence-based? And I just wanted to say absolutely you should still be creating evidence that the argument you have followed has been, that there is things you have done to meet these, whether that's in your data gathering, your model construction, your assessment, your evaluation, your metrics. So yes, it would all still be very much, and that comes back to what Mark was saying about having logs that show we didn't just come up with a model and we think it's all fine. We have evidence that what we did was appropriate.
And you know, it is literally back to, you cannot manage anything if you don't have a baseline and you don't have some idea what good looks like. It's just literally impossible. And we know we've got to do this operationally. So you've got to put the evidence together so you can challenge it. You know, we'd like it to be really good evidence, but if it's bad, we can still challenge it very fast if we know what it is when the ground truth really hits it. That's the fundamental thing we need. That's why it has to be evidence-based rather than arm-waving, because otherwise we're back to relying on experience of human beings to go, but it doesn't feel right today, and it ain't gonna work for these complex systems, because the human won't be doing that, because they won't have that experience.
Thanks very much.
That's one of my bugbears for today, so I'll leave that.
Thanks very much again, Mark, for the insightful talk and these answers. I think we'll leave some of the questions unanswered because we are running out of time, but please approach Mark by email for further questions about his talk.
Absolutely. This is supposed to be an overview of the state of the world, and therefore hopefully did generate a bunch of questions.